I'd like to present a few key design principles that I've learned, which I believe could be applied to solving a range of different problems. I know you're all excited to listen to the engineer in the room, so here I am. But I'll kind of present these design principles, and I believe they can be applied to a range of problems. And I'll kind of do it through a case study of a new total lumbar, new advanced interbody lumbar device that I've been working on developing. So, great. So first of all, when we're designing something, we want to first figure out what's the opportunity, right? So lower, and you guys know this, lower back and neck pain has become so pervasive that it has been characterized as the most disabling condition in the world. So fusion is currently one of the most commonly used surgical options for treating a range of spinal disorders, but has been shown to lead to a higher rate of adjacent segment disease, or the rapid degeneration of the adjacent discs when compared to motion-preserving options. So currently there are 2 FDA-approved disc replacement options in the USA, and while these devices do preserve motion, the resulting movement and stresses differ pretty significantly from those of a healthy disc replacement, of a healthy intervertebral disc. And this discrepancy presents an opportunity to develop a unique mechanism that better mimics the biomechanics of a natural disc. So now on to the whole design principles. The first principle is, first principle is thinking. So have you ever heard someone say, don't reinvent the wheel? In our technologically advanced world, we often approach a problem with a set of assumptions, and we take those assumptions as fact. I believe that some of the greatest solutions actually come about when we question those assumptions and begin from the basic principles regarding the problem to be solved. So many of the current disc replacement devices, including all FDA-approved devices, have carried over this ball and socket design used to replace diarthrodial joints in the body. Notice the similarity between the hip replacement device and the total lumbar disc replacement shown. These ball and socket devices have shown to be safe and effective, giving many people a surgical option that retains motion in the spine. However, studies have shown that these devices do change the biomechanics of the spine and can result in higher stresses on the surrounding structures. Intervertebral spinal discs are biomechanically very different from diarthrodial joints. A solution that begins with the basic biomechanics in these joints rather than beginning with an already existing technology would likely prove beneficial. So with my team at BYU, we've developed a mechanism that combines a flexible spring-like geometry with rigid bearing surfaces that cause the device to roll in flexion extension and lateral bending. These spring-like or compliant flexures give the mechanism the same stiffness properties that exist in a healthy disc, while the rigid bearing surfaces support the substantial compressive loads in the spine and give the mechanism a mobile center of rotation as exists in a healthy lumbar disc. So the second principle that I'd like to talk about is to capitalize on your strengths, or as ChatGPT also suggested, exploit your capabilities, harness your skills, or optimize your potential. So there are many ways to make a disc replacement. There's many ways to design just about anything. But rather than chasing every good idea out there, we decided to focus on a solution that played to the strengths of the members on our team. So this includes Dr. Anton Bowden at BYU. He's an expert in biomechanics. Many of you know him. His experience researching and analyzing the movements and forces of the spine were central to our ability to design for this complex joint. Feedback from Dr. John Edwards, which of course we all know, was crucial, and he's performed thousands of spinal procedures, including fusion and disc replacement, and his feedback gave us crucial clinical insight into the practical usage of the various concepts that we developed. My abilities are primarily in mechanical design, particularly in the fields of compliant mechanisms, which is that spring-like geometry. Dr. Ron Anderson also participated. He spent his entire career with hip and knee implants and provided additional clinical perspective on various material and geometrical considerations. And then finally, we had a team of incredible undergraduate researchers. And by recognizing the strengths of our team, we could deliberately choose not to explore solutions outside our set of capabilities, such as those possibly involving tissue engineering or advanced materials, but instead we concentrated on areas where we could excel beyond all others and develop what I believe to be a very good solution. So this is a fun animation. It shows the process that we followed to develop our concept through computer-aided design. It's a core strength of multiple members of our team, and the tool allowed us to quickly visualize and analyze a design concept. Okay, so the final principle is to fail forward. So some people say that Thomas Edison failed over 1,000 times before he was able to make the light bulb. I have learned to expect failure throughout the design process. Fortunately, I have yet to go through 1,000 iterations, but I know firsthand that it takes a lot of humility to accept that a seemingly brilliant idea that I've developed has flaws and needs to be addressed. But when I approach a problem as a learning process, then each failure can be a valuable lesson that pushes me closer to success. So going along with that, this is an animation, a time-lapse video of a 3D printed device. So 3D printing was a crucial skill that, again, various members on our team brought to the table. And the capability allowed us to rapidly prototype our ideas, enabling us to fail fast and fail frequently. This is finite element analysis, and it's a mathematical method of analyzing the stresses in a 3D object. Like 3D printing, we were able to use this tool to perform in-depth mechanical analyses of our designs prior to any costly or time-consuming prototyping. Now, for those of you wondering, this is version number 13, which we have now prototyped in titanium, and the design continues to be tested, and the process is, of course, ongoing. So, key takeaways again. Don't be afraid to reinvent the wheel when approaching a problem. Know what assumptions are being made and question them before moving forward. Capitalize on your strengths. Focus on solutions that emphasize your skill set and those of your team. This will enable solutions that you are uniquely capable of developing. And finally, fail forward. Continually testing and honestly evaluating each solution is crucial to creating a truly value-adding outcome. Thank you.